Hello, welcome to lesson 25. Today we're going to be solving equations with logarithms in them. We just did some work with exponential. Now we're going to extend that and kind of focus on our logarithms a little bit. Now to start out with, I thought, well, where do we use logarithms? And actually our science people like to use logarithms quite a bit. And I went along the direction of the earthquakes, especially with the event in Haiti not so long ago. It's kind of in the news. Well, here in Missouri, we had a huge earthquake. It was actually a series of quakes between December of 1811 and February of 1812. And they registered from a 7.2 up to an 8.1. I think the first event was 8.1, and then aftershocks got as high as 7.2. And I pulled out this information. By the way, the site where I pulled all of this was the U.S. Geological Service from the U.S. government. Off the coast of northern Sumatra, I came up with about the highest Richter value I could find of a 9.1. And over 227,000 people were killed in this one in 2004. The one in Haiti had a Richter value of 7.0. So we see these numbers for earthquakes, and we all see them in news, but what do they really mean? Now, by the way, let me tell you right now, I am not a geologist. I am not an expert on Richter values or earthquakes, seismology. I think you probably want to contact them. What I'm going to do is just give a everyday person's idea of this, okay? I'm not hitting the science hard. So, one basic way you can view these Richter values is that it's a common log. Now, there isn't a base written here, so our base is understood to be, what? 10. Base 10 if it's not written. And the I sub E would be the intensity of that event, which of course they're using instruments to measure. And the I sub B is the intensity of some baseline. Now, one way you might view it is that that baseline is about the mildest one that we might be able to pick up. Gives you a rough idea. And so the question that I ask you is, how many times stronger was this Sumatra event of a 9.1 versus the Haiti earthquake with a 7.0? Because those numbers don't seem to be that far apart. So are those about the same kind? Well, let's use our understanding of logarithms. We know that for Sumatra, the log of the intensity of that event compared to the intensity of the baseline is going to equal 9.1. This is where our Richter value is going to go. Well, then you recall properties, actually definition of logarithm. Since this is base 10, 10 raised to the 9.1 is going to equal the intensity of that event compared to the intensity of the baseline. Now, I don't know either of those values, but what I can do is say the intensity of the event is approximately 10 to the 9.1 times the intensity of that baseline. Okay? Well, I can do the same thing for Haiti. And for Haiti, I would have the log, the intensity of the event in Haiti versus the baseline is equal to 7.0. Okay. And then 10 to the 7.0 times that baseline is going to be the intensity of the event. So then if I wanted to compare these, the question is, how many times stronger? Well, if you want to know how many times stronger, that means you're going to divide. So the intensity of this event is 10 to the 9.1 times the baseline. The intensity in Haiti was 10 to the 7.0 times the baseline. And you know what's kind of interesting here is that baseline does not matter at this point in time. I simply cancel these guys off and I say, well, it's going to be 10 to the 9.1 divided by 10 to the 7.0. And so I actually get 10 to the 2.1. Okay? Now I know you look at that and say, well, what does that tell me? Well, I didn't put the number here for myself, and I wish I would have, but that is going to be something over 100, because you know 10 squared is 100. So this is going to be somewhere in the neighborhood of 120 or something times more intense. So that event in Sumatra was very serious. What that means is that a small change in that Richter value actually has a big impact on how intense that earthquake was. Now, by the way, notice that essentially what we could have done from the very beginning was subtract those Richter values. And what's interesting about it is, think about why is it we could have subtracted it. Because look at what happened, and this is just a review of how well you understand logarithms. Notice that our logarithms came up here as exponents, because I tried to stress logs are exponents, logs are exponents. And because it was a division situation, then I ended up subtracting it, okay? And after subtracting it, because I'm in base 10, it's actually 10 raised to that exponent times stronger. Okay? So then I asked the question, I went for something recent. February 10th of 2010, there was a quake with a magnitude of 3.8 in nearby Illinois. Now, how many times stronger was that event in New Madrid way back in the 1800s? Well, let's see here. New Madrid had a Richter value of 8.1, whereas this is a 3.8. So if I simply do that subtraction, now I'm subtracting my Richter values because they're coming out of logarithm, they are exponents, and I'm actually wanting to divide. So I subtract my exponents and I get what, 4.3? So 10 to the 4.3. Wow. Now I forgot to bring the calculator, but you know that 10 to the 4th is what, 10,000? So you're looking at somewhere seriously more than 10,000 times more intense. Again, it just helps to illustrate that it doesn't take a really big difference in the Richter value to have a huge difference in how intense that earthquake actually ended up being. Okay? Now, let's leave that and just go ahead and solve some log equations because I think we've mentioned this before maybe. Your logarithms are going to be used in the case of the earthquakes. They're used for pH scales. They're used for the decibel scale. So there's a lot of times that we're actually applying logarithms, and then you need to be able to, if you're working in those areas, deal with equations that have logarithms. And they basically come in two kinds. So here's the first kind. I said we're going to solve these guys using our log properties and using the basic definition of logarithms. Now I said that I'd like to have those answers as exact values and go ahead and give an approximation. Okay? Now in this particular case, I come upon this equation and I look at it and I think, you know, since I know what logarithms are all about, I can do this. This is as simplified as I can write it, so I can actually then use the definition of logs to say 5 raised to the exponent of 3 has to equal x plus 7. Agreed? Now, if you're rusty on that, then you might want to pause me for a minute and run and check that definition of logarithms. Okay. Well, that's what 125 is equal to x plus 7. So subtract the 7 away, and we get 118 is what x should be. Now, by the way, I also put a warning up here. Be sure when you're working with logarithms to take a quick look back with your answer, because we have to keep the input to the log function always positive. Remember the graph of the logarithm? The graph of the logarithm function comes from down here. He has an asymptote. He crosses at 1, 0 and goes on that direction. What that is a picture of is the idea that the domain is positive numbers only. So don't tell me that I should take a negative value and put it in to the log, but this answer is totally fine. Okay, so I'm good with that guy. And I go on to the next one, and I see that I have a logarithm, and I see that my variable is sitting inside of that log, which means that to get the variable by itself, I'm going to have to pull it out of the log, but I can't just randomly do that. So the first thing I want to do is remove the outside items. You know the 6 and the 4 can be taken away, and in fact, think about it for a second. Which one should be moved first? Well, we always take the outside guy. So subtract that 4 off, and we have 6 log x is equal to -3. Now, by the way, you might be saying, whoa, wait a minute, a negative. No, we're okay here. That negative is an answer coming out. And, well, my graph is gone. There it is. The answer coming out can be negative. It's just that I cannot put a negative number into the log. Okay? Well, I got the 4 moved. Now it'd be a good idea to move that 6. So dividing that 6 off, I have log of x is equal to -1/2. And now I have done all the simplifying over here on the left that I can possibly do, and I have to get that x outside of the logarithms, and the way that I do that is using the definition. Remember that that is a base 10, so 10 raised to the -1/2 has to equal x. And you say, what? Well, remember what the negative does? The negative tells you to do a reciprocal right in that particular spot and make it a positive exponent. And then you consider, well, a 1/2 as an exponent? That seems odd. Well, that's the square root. Now, that would be an exact answer. I know some people like to rationalize the denominator, but I'm okay with leaving it as a 1 over square root of 10. Now, to make things a little bit easier, I did also go ahead and pre-work to get an approximation. It's not one I was going to easily run in my head. We get a 0.32. And then you take a second and look back. Is it okay for me to put 1 over square root of 10 into here? Now, by the way, some people will say, well, you didn't need to check that because that wasn't a negative number. Oh, but be careful. It's not so much whether this number is positive or negative. It's a matter of the input to the log function has to be positive. So, for example, if my input had been x minus 7, well, if you put in a positive 0.32 and you subtract 7, you have a negative number. So my point is this. Don't just dismiss positive numbers and think, well, I don't have to look at that. No, be in the habit of always looking back when you're working with log equations, okay? Because just when you don't is when you should have, or at least that's my experience. Okay. Well, when I look at this guy, and you know I'm trying to solve it for x, get the x by himself, I notice that he's sitting just right here. I've got some outer numbers that can easily be removed, so do that. So subtracting the 7 off, 3 natural log of x is equal to -1. Natural log of x is equal to -1/3. So now the easy stuff is done. Now you have to stop and think about the fact that this is, first off, a logarithm, and secondly, the ln tells me, oh yeah, it's base e. So coming out of the logarithms using the definition. I want you to use good mathematics, not just, oh, I think that's what I'm supposed to do. Because you understand what logarithms mean, e to the negative 1/3 equals x. Now technically you could leave that as your exact answer. Of course, if you want to be real snazzy-dazzy, I guess you could say 1 over the cube root of e. Ooh, why did I do 1 over? The negative. And where did this cube root come from? A 1/3 power. Okay? And then I came up with a decimal approximation of about 0.72. And I take a second and I run them back and say, okay. Now, by the way, did I verify that I know my answer's right? No, I didn't do that. In order to do that, you actually need to run your values, and if you put it in as e to the negative 1/3, it makes it pretty easy. Let's just go ahead and do that. Does that equal 6? Well, we want to look right here first. I have 7 plus 3 times. Now, natural log of e to the negative 1/3, ooh, that's one of those scary things. Well, you might say, well, I could bring that 1/3 down, the negative 1/3 times natural log of e. Some people like that idea. And what does the natural log of e equal? Well, since that input is exactly the same as the base, that's 1. So we have 7 plus 3 times negative 1/3. Will that equal 6? And you take a second and look at the arithmetic and say, yeah, that works. Now, that's actually verifying that I have the correct answer. When I keep saying, you know, look back, I'm just making sure that I'm not giving an unacceptable answer, okay? Well, now what's suddenly different in this case? As I look at this problem, it's like, whoa, I've got x appearing here, but I also have an x appearing here. Whew. And there's a couple of routes that you might follow, but I'm going to take a particular one. I notice that I have addition of logarithms, and something else that I must make a note of is that they do have the exact same base. They have to, in order for me to apply these properties. Since they're both base 2, it is addition. I can use the property of logs that says, oh, then your inputs were multiplied. Right? One of the properties that we studied in a previous lesson of logarithms. Well, then, if you want to do the multiplication inside of there, log base 2 of x squared minus 1 is equal to 3. And now I've pretty well exhausted the basic steps that I can take. Now I need to address the situation that my variable is inside of the logarithm. Using the definition, 2 to the 3rd power has to equal x squared minus 1. Right? Well, that's an 8. So 8 equals x squared minus 1. 0 equals x squared minus 9. Now, some of you are going to say, ooh, I would do that differently. Well, that's fine, except I've got the marker. So we'll do it my way. I'm going to go ahead and factor this. There are other alternatives. But sometimes factoring is safe because you clearly see, oh, there are 2 answers. Setting each of those factors equal to 0, remember that zero product property from way back when? X is 3 or X is -3. Now, are two answers acceptable? Well, maybe, maybe not. Let's try to put them in and see what happens. If I put the 3 in, I have log base 2 of 3 minus 1, 2, plus log base 2 of 3 plus 1, which is 4. Will that equal 3? And if you take just a minute, you might realize that's 1, that's 2. Yay, it works. Okay, so what if instead I decide to put the -3 in? Okay, so let's see here. -3 minus 1 would be -4. And -3 plus 1 is -2. And then you'll look at that and say, wait a minute, I can't do that. Which means that we must reject that answer. And the only answer that we're going to take in this case is the 3. Okay? And I went ahead and wrote that all up just to make sure that we didn't overlook anything. X does pop up to be plus or minus 3. However, now sometimes you take both answers. But in this particular case, X can't be -3. Now why? Do you reject every negative value you get? No, you do not. What you do is you check them back into the original. And if it would make your input negative, that's what makes you reject it. And so we take simply X is 3. Okay? Just don't want you to be sloppy. Okay? Looks like the same kind of a setup here, except I've got a subtraction property going on here. Well, what does subtraction tell me has to be happening? Like division, right? Okay, so let's see. I can combine these two guys right now and say log base 4 of the positive term divided by the term following the subtraction. Okay. Oh, it's a little scary seeing fractions, but we'll live with it, right? And now, I can't really do anything nice with that input, so let's come out of the logarithms using the definition. So 4 raised to the 1/2 is going to equal x plus 2 over x minus 1. Right? So 2, where did I get to? I didn't take 4 times 1/2. It's 4 raised to the 1/2 power, and the 1/2 power is the square root. Square root of 4 is 2. Okay? And then as you ponder with frustration that you have a fraction, you realize, okay, well, either I can think of clearing my fractions, or I can really think that this is a big proportion and kind of cross multiply. It's the same thing. So we end up with 2x minus 2 is going to equal x plus 2. And so we went from a pretty ugly mess to a very easy equation to solve. So we get what? X is 4. And I immediately take a second and say, can I take a 4? Well, 4 plus 2 is 6. 4 minus 1 is 3. Yes, I can take it. Okay? So I'm good with that particular result that x is 4. Okay? Okay, now we've got a slightly different setup. Do you see here what's different about this particular guy? I got a number inside of the log over here. and I don't have any numbers that aren't in the log. Now I know you might say, well, the 3 isn't in the log, but the 3 is attached to this log. There's no other terms here that are, simply numerical, okay? That is numerical, but we're going to run this 3 up, and I would have log of x cubed is equal to log of 8. You know, sometimes in algebra, when you come upon an equation and you're not 100% sure what to do, you start thinking, well, what can I legitimately, mathematically do? And you go ahead and make that move in the hope that where you end up is suddenly a place that you feel much more comfortable and you can say, oh, I know what to do. Meaning this. The fact that I moved that 3 up, that was one of those properties of logs, and then I look at this and I say, you know, that's kind of interesting. If these two guys are going to be equal to each other, then does x cubed have to be equal to 8? You know, I don't want you to jump to any inappropriate conclusions. There is a very good reason why that will happen. Remember that graph of the log function I showed you just a few minutes ago? That particular guy is what we call 1 to 1. All of our log functions are 1 to 1, meaning that they pass the horizontal line test. Anywhere I would draw a horizontal line, I will only cut that curve in one place. Now that means that if these two outputs are equal, the only way that can happen is if they have the very same input, because they're 1 to 1 and every output has a unique input. So it is totally legitimate. I am not dividing off the logs. I am not subtracting off the logs. And I'm certainly not erasing the logs. What I'm doing is using the fact that the logarithm function is 1 to 1. So if the outputs are equal, the inputs must also be equal. Okay? That's our second type of log equation, by the way. The first kind is when we're going to use our definition in order to come out of our logs, because it's pretty hard to completely solve the problem in the logs. A lot of times we've got to pull the variable out. And in this case, we use the idea that if I can get these logs to be equal, then I can pull those inputs out. They must also be equal. And if x cubed is 8, x must be 2. And I take a quick look back, I'm okay with that. All right? So that's the basic idea here of what we're going to do with this second kind. And I look at all this and say, wow, I got logs everywhere. I'm not ready to come out of the logs because, you know, that idea that I just used was that if the two outputs were the same. Well, I got 3 outputs here. You're not ready to do that yet. You don't just erase the logs, okay? But as I look over here, I say, you know, I can use my log properties, can't I? I know that if 2 logs with the same base are being added, that means the input. Hey, what are logs? Logs are exponents. And if those exponents are being added, then we were multiplying. Oh, yeah. So I'm leaving the left side just as it was. And on the right-hand side, I'm going to multiply these two inputs together, and I get 3x minus 15. Okay? And then I look, and you know, it doesn't matter what the base is, as long as these two bases are the same, then if those outputs are the same, that can only happen if the inputs are the same. Okay? So what? 2x is equal to 14, I believe. X is 7. 7 minus 1 would be positive. 7 minus 5 would be positive, which means I do not automatically reject this answer. Now, do I know it's right? No, I'd have to check it by actually running these values, okay? But it is an acceptable answer. Okay? Well, let's see here. I only have one log. That's an encouraging thing. Oh, but he's inside absolute values. Well, you know, common sense just tells you isolate that absolute value first. You know, that's what we did when we just had like a plain x inside of that absolute value earlier. So I could add that one over, subtract the 2, and have 4 minus 2 is equal to the absolute value of log of x. So the absolute value of log of x is going to equal 2. Now you might say, oh, come out of the logs. Oh, but I got a bigger problem here. Remember, you can never solve your problems when you're inside the bars. Yeah. So I have to first deal with the fact that this is inside of the absolute value. I need to handle that part first. So if his absolute value is equal to 2, then what does that mean this could be? Doesn't it mean that log x could be negative 2 or log x could be positive 2? Know what it means? Because the absolute value of negative 2 is 2, absolute value of positive 2 is 2. Okay. And now you notice that this is different than the very last problem we did. I don't have a log on both sides. So I'm not pulling inputs out. What I'm going to do is use the definition. 10 to the negative 2 is equal to x. So using that negative exponent, that would be 1 over 100. Or 10 to the 2 is equal to x. X equals 100. So that's kind of interesting. X is either 100 or it's 1 over 100. Are they both acceptable? Yes. And in fact, if you double check, they're both going to work and give you a correct answer. Okay? So basically here, as we try to boil down solving your log equations, there's two big kinds of equations that you're going to be dealing with. Okay? If one side of your equation does not have, now by the way, that means you probably want to collect things as much as possible. You want to remove any extra numbers that you can get moved around. But if you have one side of the equation that does not include the log function, use the definition to come out of the logs. Okay? If you get it boiled down to where you have one log is equal to another log, same base, then those inputs have to be equal. We are not subtracting logs. We are not dividing log off. We are using the concept that logs are one-to-one functions. And we're going to pull those arguments out, set them equal to each other, and we're good from there. Also, don't forget to check those answers back because in particular, logs can give you just that little bit of grief that sometimes you get an answer that you cannot accept. Okay? Well, have fun practicing solving log equations, and I'll see you in the next lesson.